So I went out to the composting bedding pack barn. This is fall, so it's actually 12 months later after we started the trials of the aerated static pile, Johnson Sioux, and Jerry Gillespie Spice anaerobic pile. You can see the actively turned windrows in the background, which is what the farm is doing right now. By the way, that piece of equipment, orange piece of equipment, is a round bale chopper and blower, so that's what they use to blow in. Actually, 3 round bales a day is what it turns out to be, and I did the math on that just a couple days ago, and it's about a 30-to-1 carbon to nitrogen ratio, so it's decent. So that's why their windrows are turning out fairly well, pretty good. They're actively turned windrows. So right here, what we have on the left, this is the aerated static pile windrow that I covered in bark mulch, about a 6-inch layer of bark mulch. And they blew that for a few weeks at least. I don't remember exactly how many weeks it was, but until the temperature wasn't increasing anymore or staying high, even though were adding in more air. I think it was something like, 15 seconds, somewhere between 15 to 30 seconds every 30 minutes is what they were doing. On the right here, this is the Jerry Gillespie windrow, and we actually blew that for the first week, and then we decided to switch up and try and do a Jerry Gillespie anaerobic pile. So we dumped on about, I think we mixed up a 5-gallon bucket of his inoculant. That's fermented. You start with fermented rice and add in milk and ferment that and so on. So according to his directions, you only need 1 quart for every 13 cubic yards. So really, we only would have needed like maybe 1 quart on that whole pile. But we did not mix in the inoculant. Like I said, we just dumped it on the top. That was our mistake. I didn't read the directions well enough. Also, I thought that the pile was still fairly, fluffy or not compacted that much, and that with the larger volume of this spice compost or inoculant that was dumped on there, that it would be all right. But as it turns out, let me play this video. Like I said, I went back and I dug into the side of these piles just to give you a sense of what it looked like. So this aerated static pile actually did well. It had a nice fungal smell to it. When I looked at it under the microscope, though, I did not see much fungal hyphae at all, which kind of surprised me. By the way, just as an aside here, I'm pointing to little white patches and in a couple places, and this is actually fairly deep into the pile in terms of moisture, so this material is still damp. I would put it in the friable moisture level. Damp, but definitely not at a 60% moisture content. And what people often confuse in their compost piles is they'll get this bloom of white substance, generally between, let me show you a picture of this, generally between the layer of dry material and where it starts to get damp. And this is usually an anaerobic layer there, and that is either Actinobacteria or Actinomyces. That's also a bacteria. So that is not fungi, is my main point. And by the way, this stuff is not good for you, so don't breathe it. And if you've got open cuts and stuff like that, don't expose yourself to that. So yeah, that's what I'm pointing out in the pile. But like I said, when I looked under the microscope, I did not see much fungal hyphae, although I'll show you the labs. We had PLAF or FA labs done by Ward Labs, and I'll talk about that in just a bit. But here you can see I'm digging into the pile, and it's still moist. You can see, by the way, take a notice of, the number of wood chips that are still in there. It's significant in terms of the total amount, and that's going to come into play later on. But what was also interesting about that pile was the aerated static pile is there were areas where there were like more dense clumps, I would say, and the material wasn't broken down quite as well, although it smelled fine. And they do say, we have heard in other videos of larger operations, where they will pull the piping and then they'll actually turn the pile once to let it, quote unquote, finish. So this is the anaerobic pile. Sorry, I didn't do any videos when it was actually covered and stuff, it was just didn't happen. But it's hard to see in this picture, but this material is much denser and compacted, and there are parts where it's actually greasy. And when we pulled apart the pile, it had a smell to it. There were chunks in there, maybe again, 1 cubic foot, where it was definitely anaerobic, smelled bad, although other parts of it seemed decent. So I think that in large part was not getting that mixed in, not getting that inoculant mixed in there well. So I also want to jump over now to this other video of, this is our Johnson-Su material, and this is actually, again, a year later now, and in spring we used this in our extract trials, but you can see even now, the material is definitely drier. It's more at like a friable nut state. You can see it's just loaded with our native earthworms. But also, if you look at it, again, you can get a sense for, the number of chunks of wood chips, not as much as in the aerated pile, but definitely a lot of wood chips in there that didn't get broken down, which, like I said, I want to talk about when I look at these labs. So I've put this in a table, and you can actually go to the BEAM, BEAM website, and they have what are called PLFA labs done by Ward Labs, results showing on their website. That PLFA stands for phospholipid fatty acids. Don't ask me how that all works. I don't know. But, here in these two tables, I've put the results, and BEAM is the really good stuff that you can buy online. And I think David Johnson is associated with them, although I'm not exactly sure. This is our aerated static pile results, and then this is our Johnson-Su results. And what's interesting, first of all, if you look at the total living microbial biomass in nanograms per gram, so for every gram, this is the amount of total microbial, biomass is a good word for it. So bacteria, fungi, protozoa, and so on. And the BEAM, it's 31,000. In our, you can see that we're significantly less. So even if you double the numbers, which I'm saying we can easily do because we did not screen our wood chips out when we sent in our samples, which was a mistake because, of course, the BEAM compost doesn't have any wood chips in it, so we're not doing a straight up comparison. And also, I should mention before I go further into the discussion on the results is that David Johnson himself has said that the PLFA labs are good for checking to see how you're doing in terms of your compost. So year over year, if you're improving, if various changes you've made are helpful, but not useful for comparing composts from one location to another. So, still, nonetheless, I think it is informative and worth taking a look at. So, we've got a lot less total microbial biomass. And why is that? Like I said, even if you double the numbers, we're way less. I'm not sure, because isn't compost food? Why are we getting so much less? Except when you look over here, you see that their total fungi in nanograms per gram is just off the scale high. So when you take that into consideration, that is where this extra biomass is coming from. So they've just got a huge amount of fungi. And like I've talked about in other videos, they have a very high carbon. David Johnson uses a very high carbon to nitrogen ratio. So I think that's where that's coming from. And then in terms of, this functional group diversity, which here's the charts they show in the lab work. What's interesting is there's not as much diversity in the bean compost, and I think that's because it's pretty much broken down. Although I'm kind of shooting from the hip here. I'm just trying to figure out these labs. Total bacteria, if you double our numbers, for our Johnson-Su it would be about the same, but more in the aerated static pile, which is consistent with what I was seeing. So when I looked at our Johnson-Su in spring, there was a good amount of fungal hyphae under the microscope. Later on, when I looked at it again, 12 months in, there wasn't any, which is consistent with what David Johnson is saying, and that is that, the fungal hyphae, the fungi go through the pile, and that's when you're going to see your fungal hyphae, but later on die out, and when they die out, they sporulate, so they put a lot of spores in the compost, and that's actually what you're putting in furrow, and I think is so important. David Johnson, again, I mentioned this in another video, but he was saying that they like to see between 5,000 to 15,000 spores per cubic foot applied as an extract in furrow. So it's just a huge amount. So again, if you look at, the percent of fungi as the total biomass, if you double our numbers, we did pretty good. But I think our Johnson-Su was really short on the fungi because it hadn't totally cooked. So we had to dig into the pile I think it was at 8 months rather than a year. And also the material that we provided, that we did not provide enough carbon, which is what the fungi are going to break down. And the last interesting thing is that, if you look at protozoa, so I'm going to do some videos on microscope work, and protozoa are like nematodes, amoeba, protozoa, nematodes, amoeba, I can see them in my head, okay, ciliates, and flagellates, things like that. So they are larger predator that eat bacteria or the prey. So in the bean compost, it's all prey. And if you were making a tea, that would be terrible tea because, you're trying to get these upper level microorganisms, the predators, the protozoa. But in terms of the bean compost, I think it's all prey because it's gone through that entire process. So at one point there were, I'm sure, a lot of predators, and then they just basically consumed everything. And what you have left now are bacteria in cyst forms, and fungi in spore form. So that's kind of what I can glean from the lab work.